Me, you, we, do, re, mi, fa, sol, la, ti, do. She sells seashells at the seashore. No. She sells seashells at the seashore. The big black bug bled black blood. How many cats can a cat scan if a cat scan could scan cats? Peter Piper picked a peck of pickled peppers. All right, I guess we're ready to start and record, and we're off. All right, class. Today, our topic is concepts of physics and rehabilitation. So there's our good friend Sir Isaac Newton. Our objectives, as usual, we want to display an understanding of force and examples of internal and external force. We want to explain the relevance of Newton's laws of motion to therapeutic exercise. We want to explain how center of gravity changes with movement, the relationship between center of gravity, line of gravity, and base of support, and display an understanding of levers and how changing length of lever arm can affect the body's reaction to gravity. And then display understanding of length tension curve and the relationship to therapeutic exercise. And finally, the relevance of elasticity, stress, strain, creep, friction in therapeutic exercise. So let's start with force. Force is energy that causes movement, and it has direction and magnitude. So our equation is force equals mass times acceleration. So we have internal force, which is created by muscles, and external force, which is created by outside forces acting on a body. For example, gravity. You jump off the roof of the building, your body is going to be acted upon by gravity, which is going to rapidly take your body towards the ground. Or if, let's say, you're a running back and you have the ball running up the middle of the line, there is an opposing player that's going to act as an outside force acting upon your body. So let's talk about Newton's laws of motion. The first law of motion is a body at rest tends to stay at rest, a body in motion tends to stay in motion. We typically call this inertia. So we see that in weightlifting. Once you get the bar or the weight moving, it continues to move. It's that overcoming inertia that's the big problem, that initial getting it off your chest or coming up from a squatting position. The second law of motion is acceleration of an object is directly proportional to the force causing the motion and inversely proportional to the mass of the object. So we see that in somebody that's big trying to throw a shot put versus somebody that's small trying to throw a shot put, or how you can throw something with very little mass as hard as you can and it barely goes anywhere. So if you have a wiffle ball and you try to throw a wiffle ball compared to a baseball, the baseball has more mass, it's going to go farther. The third law of motion we're pretty familiar with. Every action there is an equal and opposite reaction. See that a lot in plyometrics. So if we're using a plyo back, we throw a weighted ball into the plyo back, and it's going to return that ball to you. The harder you throw it, the quicker it's going to and harder it's going to return it to you. So let's talk about some terms here. We have center of gravity is the point at which a body is balanced. The line of gravity is a vertical line through the center of gravity. The base of support is a two-dimensional area between an object's points of contact. And lastly, stability, which occurs when a line of gravity falls within base of support. We'll look at some videos in lab that help us to see how the center of gravity will change the line of gravity, which then will impact our base of support and our stability. Now, body levers. A lever is an object that can multiply mechanical force or effort or resistance force or a load. A lever arm is the distance from the axis of rotation to the line of action of the force. So we have three classes of levers, and we see these in our body, and the pictures give you an example of the lever and the body part. So the first class lever is a fulcrum is located between the applied force and the load. So we see this at the elbow. So the fulcrum is the elbow joint. The load we would put at our hand, and our effort would be our triceps muscle. So this would be like doing a triceps extension, like a nose buster, where we have weight in the hand. We're laying on our back. The upper arm, the humerus is vertical, and we straighten out the elbow. So the load is distal to the fulcrum. The fulcrum is between the load and the effort, or the load and the force. Second class lever is a load situated between the fulcrum and the force. So we see this with the gastrocnemius and the ankle joint. So our fulcrum is at our toes. The load is going anterior to our ankle joint, and our effort is coming from the gastrocnemius going in the opposite direction. So the force and load are going the opposite direction, both distal to the fulcrum. The third class lever is a force applied between the fulcrum and the load. So we see now with the biceps. So if we flip the arm back over, and now our load is still at the hand, and the fulcrum is still at the elbow joint, but now the effort is, or the force is in between the fulcrum and the load now. So this being the biceps muscle doing a biceps curl. Torque is the ability of a force to cause a rotational movement or angular motion. Product of force and length of the lever arm. So the equation is torque equals force times length. And let's see, all joints of the body produce angular motion, but the result is usually a linear motion of the body moving forward. It's measured in Newton meters or foot-pounds. So torque, somebody a long time ago was smart enough to put the hinges of the door on one side and the door handle on the opposite side instead of putting the door handle right next to the hinges. So we can open the door without using much force because the length between the hinge and the door handle gives us torque and gives us a mechanical advantage on opening the door. Let's talk about a length tension curve. So the muscles not only have a mechanical advantage, but a physiological advantage. So that, as we well know, muscles shorten and elongate. So the length tension curve occurs when the muscle is at a resting length, as a condition of rest and no tension or no stretch on the muscle. And a muscle is able to shorten about 66% of it, or 2/3 of its resting length. So here's our length tension curve. So you see right there in the middle the optimal resting length as number 2 there. And then as it decreases going to the left and increases going to the right, you see force production or tension, which is on the left side, the vertical axis, as it dramatically decreases once you drop off from the optimal resting length. You see the normal range of the muscle length there at the bottom in the bottom box. Outside of that range, to the far left, you see that you're not going to be able to generate any force at all once the muscle becomes over-shortened. Likewise, on the opposite end, you're not going to, as the muscle over-lengthens, you're not going to be able to generate any force. So we want to be able to use a muscle kind of in that mid-range there, where it's going to be able to produce the most force. We see this specifically at the wrist. So as your wrist is in neutral, you can generate a lot of force with your grip. If you break your wrist over and you flex your wrist, now you cannot generate much force at all. You go the other direction and you extend your wrist, and you're not going to be able to generate much force either. So we want to be able to use this knowledge to our advantage as we set up our athletes in our exercises and doing exercises that we feel that they need to do, or the optimal way for them to do an exercise. So talking about multi-joint muscles, you can have active insufficiency or passive insufficiency. So active insufficiency is a muscle is incapable of shortening any further. So it's shortened as far as it's going to go, and that's all it can do on its own. Then you have passive insufficiency, and the muscle is elongated over the joints it crosses. And so now the antagonist cannot shorten anymore. So we have 3 examples here in the pictures of hamstring curl with a machine. So we see in the far left the lady laying on her stomach doing a hamstring curl. The hip is in extension as she comes up and flexes the knee. So the hamstring muscle is the one being worked. The hamstring muscle extends the leg, the lower extremity. It also flexes the knee. So her hip is already in extension. So as she flexes her knee, she's going to have insufficiency, and it's not going to, her length tension curve now is going dropping off, and she's not going to be able to generate as much force. That's the reason the bottom picture, you see how the hip is flexed, so that helps to prevent insufficiency of the muscle being able to contract. So the exercise machine on the far right, where the guy is sitting, that's going to be able to allow you to generate the most hamstring force, because now the hip is flexed, and as the knee flexes, the hamstring muscle is going to be able to maintain a good length tension curve. Elasticity and stiffness are important components of our tissue. So elasticity is the ability of tissue to resume former shape after a deforming force is applied when released. So you think of your skin as a good example of this. You pinch your skin, you pull it away, and then it pops right back in place. And we notice as we age, we lose a lot of elasticity in our skin. So you may have a grandparent that you pull the skin away and it doesn't have that bounce back because elasticity has been lost over time. We also have stiffness in our tissue, which is the ability of tissue to resist deformation when stress is applied to it. So this gives us tensile strength, and stiffness is on the opposite end of the spectrum from elasticity. And our tissue has to have a combination of both. It has to have the bounce back ability, and it has to have the ability to resist deformation as well. And then I believe we saw this stress-strain curve in our lecture about flexibility. So it's probably something important for you to know, especially on an exam, since you've seen it twice now. So stress is the force that changes the shape of a body, while strain is the amount of change in the size or shape of a body caused by stress. So this differs from tissue to tissue. So a ligament contains more elastic fibers, and newly formed scar tissue has more elasticity, which allows them to withstand more stress. So you have that elastic region down in the bottom left, and then you have this huge plastic region which causes deformation. But usually that's not the region we want to work into, or we're unable to work into that region, because at the yield point, pain usually does not allow us to go beyond that point. And then creep. Creep is not just a guy that's following you online or that keeps calling you at funny times of the night. Creep occurs when low-level stress in elastic range, when applied over time, causes tissue deformation into the plastic range. So this example, the picture on the left of somebody sitting with very poor posture at a computer, you do that long enough and you move into that plastic range where you have permanent change in the tissue. Of course, this doesn't happen overnight. This is going to be something, years and years of poor posture, that creep sets in, and now you have difficulty being able to access the opposite direction. So this example, the picture on the left, this individual sits like this long enough, pretty soon he's not going to be able to extend his head back, nor is he going to be able to extend his thoracic spine and sit up properly. And so not only does the joint change, but you can get muscular length changes as well. Now let's talk about friction. So friction is a relative resistance between two surfaces. Friction is an important component to our body, not only how we move, but how our joints move as well. We have to have friction, or we could not move and walk across the room. So a coefficient of friction is the ratio of the force that maintains contact between an object and a surface and the frictional force that resists the motion of an object. So a tire on the road has a 1.0 coefficient of friction. Teflon on Teflon, fairly slick, 0.04. And then ice on ice we think of being really slick, so that's 0.02 to 0.09. And then a normal synovial joint, though, has a really low coefficient of friction. It's at 0.001. So that produces little friction between our joints. Low friction produces low wear. So we know that we drive our car long enough, the tire, because of the friction between the tire and the road, is going to wear over time, and eventually that tire is going to wear through. Same thing happens with our joints, but at a much slower rate because we have a lower coefficient of friction. That is our lecture for today. I hope you enjoyed it. We'll do more practical stuff in lab on this, and I'll see you in class.